Okay, so in this video, I'm going to go over four examples from the last two concepts in collage. So, concept three is this idea of motional EMF. Okay, and then concept four is this induced electric field idea. So with concept three, as I said in the last video, motional EMF is basically the same. It's a repeat of Faraday and Lenz. It's just basically saying that, like, let's say you have a coil, like a solenoid, and you have a magnet. Okay, and you're moving the magnet relative to the coil. So the B field is moving. Okay. We know that we can induce a current in in that coil as a result of the moving magnetic field, right? So moving the magnet will induce a magnetic field that will oppose the change in flux, and then that will cause a current to flow through the solenoid without the solenoid being connected to any kind of power supply. So that's basically Faraday's law and Lenz's law. Motional EMF is basically saying it doesn't have to be the magnet that is moving. It could be that the magnetic field is stationary and you're moving the coil relative to it. Okay, so in fact, we saw an example like that at the end of the last video, right? Remember the one where you had like a stationary B field that you had this region in space where you had this stationary B field, right? It was just there. And then you had a wire and it was like a loop like this, and you were pulling the loop so that the flux was changing as the loop moved outside the B field. That is motional EMF. It's basically saying like instead of instead of the B field moving, the wire moves relative relative to the B field. So the B field is stationary, and the wire moves. And I mean, this is an interesting idea. And like, if you can read about this in Collage, and I've posted a bunch of videos. Like, this is how a rail gun works. This is how a satellite tether works. There's all sorts of interesting things in technology that depend on motional EMF. But I just want to make it clear that motional EMF is like the exact same principle as Faraday's law and Lenz's law. It's just like it's from the opposite, like it's looking at motion from the opposite perspective. Instead of moving the magnet relative to the wire, the magnetic field is stationary and you're moving the wire relative to the magnetic field. And there's absolutely no difference between those two situations. They're from a physics point of view, they are identical. So like I debated whether to even make this concept a separate concept. But because there are so many cool technological like things that come out of this idea, I decided to make it a separate concept, but it's the same thing as Faraday's law and Lenz's law. And then this concept induced E field is this idea that if you have a changing magnetic field, you induce a non-conservative electric field. Okay, and that electric field, that non-conservative electric field, is what creates the current that you induce when you change the magnetic field. Okay, so this idea is sort of just an extension. It's just an extension um, of Faraday's law and Lenz's law. Okay, and I've got an example that looks at this. Okay, so let's look at this first. So the first couple of examples are just building on this idea of motional EMF, if you have like um, a loop, like in this example, you've got a loop and it's rotating in a uniform magnetic field. And we want to know what is the average induced EMF and like how could we figure out like when the loop is rotating, how can we figure out like which direction the induced current will go in? Okay. So it's important to note here that the reason this is considered motional EMF is because the magnetic field is not changing. Okay. But the flux still is changing. The flux is changing because the angle of the loop is changing relative to the field, relative to B field. Okay, so again, let's write out the definition of flux. So B A cosine theta. So this is static, right? There's no change to this. There's no change to this, but this is changing as the wire rotates around in the field. Okay, so what we're going to do is we're going to calculate the change in flux as a function of time. So okay, let's write out some steps. So step one is going to be to compute the change in flux from the change in angle of the loop. Okay, so that's step one. Step two is going to be to apply Faraday's law. Apply Faraday's law. Step three is we're going to use Lenz's law to find the direction of the current. Okay, so that's pretty straightforward. Okay, so let's do it. Let's go ahead and do it. So the initial flux is just going to be B times A, so the magnetic field, which is constant, times the area, which is constant, times cosine theta. And I'm going to say that the initial angle is 0. So in other words, like if this is the B field, the loop is just like lying in the same plane so that the area vector is pointing in the same direction as the B field. Okay, so therefore the angle between those two things is 0. Okay, cosine of 0 is 1. So this just works out to B times A. So this is initial. This is the initial flux. The final flux is just going to be B A cosine 60, right? The loop changes angle from 0 degrees to 60 degrees. So I'm going to put 60 in there. Cosine of 60 is 1/2. So this just works out to 1/2 B times A. Okay, so that's step one done. Step two, I apply Faraday's law. So Faraday's law says that the change in flux is equal to the EMF. So the change in flux as a function of time is equal to the EMF. And for reasons that I explained in the last video, I like to just calculate the absolute value and then to figure out the direction with my hand. You can do it however you want, but I find it easier and more reliable if I figure out the direction based on the logic that I explained in the last video, as opposed to relying on the sign from the math. So the change in flux is going to be, so it's going to be 1/2 BA, right, is the final flux, minus BA is the initial flux, divided by the time, right? So this is 1/2 BA minus BA is actually minus 1/2 BA, but because I'm taking the absolute value, I'm just going to say it's 1/2 BA, okay, divided by delta T. And then I really just plug the numbers in, right? So it's like half times B, which is half a Tesla, times the area, which is 0.05 squared. Okay. So times pi, sorry, excuse me. So it's the area, let me just write that up here. So the area is pi, um, it's a circular loop. I'm sorry, pi r squared. So it's going to be pi times 0.05 meters squared, which is equal to 7.85 times 10 to the negative 3 meters squared. So I'm just going to plug that in here. 7.85 times 10 to the negative 3. And then I'm going to divide that by the time, 0.02 seconds. Okay. And so the EMF will be about 0.0098 volts. Okay. So, okay, so let's talk about the flux, or sorry, the induced current. So that's part A, what I just did there. A, B. Okay. So the loop starts out like this, right? And then it rotates so that it's 60 degrees relative to the B field, right? The B field stays stationary and the loop rotates. So I think it's easy to see that the flux is decreasing, right? Because here it's sort of like at its maximum, like all of the field lines are parallel to the area vector. And then as it rotates 60 degrees, um, that's not the case, right? So the flux is actually decreasing. So that means that the induced is going to um, point in this direction, right? Like to counteract that decrease. Okay. And so if I point my thumb up and I rotate my fingers, I get a counterclockwise rotation, right? If you see that, like I point my thumb in the direction of the induced current, I rotate my fingers, my fingers are going clock or counterclockwise, which by the way is a negative value. So if I had not taken the absolute value here, I think you can see that like I would have ended up with a negative number here, and that would have coincided with my counterclockwise induced current. Okay, that's problem one. Okay, let's look at problem two. So problem two, I've got a rectangular loop now. It's got a width of 0.2 meters and a height of 0.1 meters. And it moves with a constant speed of 3 meters per second into a region with a uniform magnetic field into the page. Okay, so let's just draw this situation. So I've got my uniform magnetic field, which I'm just going to represent like this. This is kind of like the opposite of the problem that I did in the end of the last video, okay? And I've got, so that's my uniform magnetic field. And here's my loop, okay? And it's got a height of 0.1 and it's got a width of 0.2. And it's moving with a V of 3 meters per second into, like, it's not in the region yet, but it's moving into the region. Okay, so again, the magnetic field is constant. This time it's not the angle that's changing, it's the area that's changing. Okay, so the change in flux is coming, like if we write like flux is the dot product between the magnetic field and the area vector. So this equals BA cosine theta. Cosine theta, we're going to assume is 0, right? So this just goes to BA because like we're going to point our area vector in the exact same direction as, so like the area vector is going to be like that. So there's 0 degrees between the two of them. So that's 1 when you take the cosine. So B times A. And this time it's this that's changing as the loop moves into the field. Okay. So, and the B is constant. Okay. So we know that the flux is equal to um, the negative of the change. Let me write it as change, not delta. The change in flux as a function of time, right? And this is going to be B times dA over dt. Okay. Um, so is that and that equals the flux, right? So this is interesting, right? How does the area change as a function of time? Okay. So if you think about like the loop being drawn in to the field, the height is staying like constant, but what's changing is how much of this is like how much of the width is changing is like going into the field. So I can express dA dt as just the height times the width divided by time, right? Because it's sort of like how much of the width is getting dragged in to the field as a function of time. And this is the same as the velocity, right? Or if you have like a displacement over time, that's just a velocity, right? So that's very cool. So you can say that this is just equal, and I'm gonna change, I'm gonna again, I'm gonna drop my sign. I just like for the reasons that I already explained. Oops. Mm, ah, B IGA over dt. I'm just gonna make this absolute value. Okay, just to make it easier. So dA over dt is just h times w divided by t. Okay, and w divided by t is just v. So it's just b h v. Okay. Um, and that's it. Like that's all there is to it. So this is the induced EMF. And this is the magnetic field is zero point 0.8 of a Tesla. The height is zero point 0.1 meters. And the velocity is 3 meters per second. Is that right? Yeah, 3 meters per second. So I should get a voltage of 0.24 volts. Okay. So that's part A. Um, what is the direction of the induced current? Okay, that's part B. Okay. So the flux in is increasing and it's increasing into the page, right? Like according to the loop, as the loop gets dragged in, the flux going through the loop is increasing. Which direction is it pointing? It's pointing into the page. So that means that the induced B field, the induced B field is going to point out of the page to oppose that change, to oppose the change in flux. Okay. So if I point my thumb out of the page, the current is counterclockwise. Okay. So that's part B. And then part C, what happens to the EMF once the loop is fully inside the field? Well, the EMF goes to zero. Once the loop is totally inside, like once it's like, let me draw it like this. Like once the loop is here, um, like as it gets dragged through, I mean, assuming it's still kind of in the field, like, right? Maybe the field extends like here. Like as long as the whole loop is in the field, there's no EMF induced because there's no change in flux. Like once it gets over here, obviously, like um there will be a induced current in the opposite direction, right? Because then the flux will be decreasing. And um yeah, so like basically there has to be a change in flux in order for the EMF not to be zero. Okay. Third question. And I mean, these questions, they're all the same, really. Like they're all, I mean, it's all variations on the same theme. Okay, so here we've got a conducting rod of length 0.5 meters slides down frictionless rails that are tilted at a small angle. Okay, so let's say that these are the rails. Okay, and I've got a rod that's like this. Well, actually, let me draw it. Sorry. Let me draw it so that it's the same length as the gap. So those are the rails, and here is the rod. Okay, and the rod is it's got a specific length. Let's just call it L, but L is 0.5. Okay, and it's sliding down, it's sliding down. The 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 rod is sliding down the rails. And we're told that there is a uniform magnetic field of zero point 0.4 Tesla pointing out of the page. Okay, so let's draw that. I'll draw that in red. So like um all like there's this magnetic field that's pointing like out of the page like this. Okay. And as this rod slides, if you think of this as kind of like a loop, right? Like an area, like a loop, that is getting the flux through that loop is changing. Okay. But we're just going to really consider the rod for now. Okay. The rod of length L. Okay. So in collage explains that when you have a segment of wire that is moving through an external B field, you can figure out the EMF just by multiplying BLV, where L is the length of the rod. Um, I want to explain to you that that is the same exact thing. That comes from Faraday's law, right? Like it's basically the same as the problem we just did. The flux is just B times A divided by delta T, right? The area of this thing, the area of this thing, area is going to equal L times like whatever incremental like X, right? It's L times X. Like let's say that this is X here, but X is changing, right? X is not static because the rod is moving to the right. So the X is increasing. So like you could rewrite this as BL dx dt, right? Because the X is not static, right? And dx dt is just V. So that's why when you have like a straight length of wire moving through an external B field, you can simplify the EMF to this formula here. But I wanted to make sure you knew where it came from. It comes from like Faraday's law. Okay, and I've dropped the sign here just because I find it easier to figure it out myself at the end. Okay. So, what is the induced EMF? Well, you can just multiply those three numbers together. So this is part A. And you can do that yourself. You got zero point 0.6 volts. Okay, part B, what is the induced current? Okay, so I can use Ohm's law again, right? V equals IR. That means that like E is V, so E equals IR. So I equals E divided by R. So that's zero point 0.6 volts divided by 2 ohms, which is the resistance. The total circuit has a resistance of 2 ohms, so that's right. And then that gives me zero point 0.3 of an amp. Okay, what is the direction of the current? Well, um, okay, what is the direction of the current? Good question, good question. So the flux is increasing out of the page, okay? Out of the page. So it's increasing in this direction. So that means that the induced B field is going to be into the page. Okay, so I put my thumb into the page, my fingers rotate clockwise, so it's going to be a clockwise current. So that means current will go like, use purple, current will go like this, right? And there has to be something here to close the loop. Okay. Um, what is the direction of the magnetic force on the rod? Okay, another really good question. So this brings us back, remember, to 2 modules ago, where we know that the magnetic force can be calculated um, by multiplying I times L cross B, right? This is I L cross B. Okay, that was from 2 modules ago. So if I put my fingers in the direction of the current, and okay, fingers are going in the direct, I'm gonna do this segment of wire here. Like, because I'm being asked, what is the force? What is the direction of the force on that little piece of movable wire? Everything else is fixed. It's this wire that's like sliding down the rails, right? That green vector is the velocity. So that rod is sliding down the rails, and the question is, what direction is the magnetic force acting on that? So like what direction is that? Okay. So I put my fingers in the direction of the current, which is this direction. Okay. I put my fingers there and I curl them in the direction of the B field. You guys see that? So my fingers are pointing down that little segment of wire. I curl them out of the page. You can see my thumb is pointing up the rails. So the magnetic force is pointing in this direction here. Okay, which means, so in answer to so what is the direction of the magnetic force? So that's part D. So it's going to be kind of like up the rails, like it's pointing up the rails, like well, I drew it on there, you can see. Okay, and so E is asking like, is the rod speeding up, slowing down, or moving at a constant speed at that instant? Well, we know it's sliding to the right down the rails, but we know that the magnetic force is opposing that. So that means that it's slowing down. The magnetic force is causing it to slow down. Okay, last question. Okay, so this one is is dealing with this idea that if you have a changing magnetic field, you automatically induce an electric field. And this explains Faraday's law. It explains where that induced current comes from. It comes from this non-conservative electric field that is generated by the changing magnetic field. Okay, so here we've got a circular region of radius 4 centimeters, and it contains a uniform magnetic field pointing into the page. Um, and it's not a constant magnetic field. It's changing at a constant rate. It's changing zero point 0.5 teslas every second. Okay. So what we want to know is find the magnitude and the direction of the induced electric field. Okay, let's write out some things that we know. Um, there are no wires here. This is just empty space. Okay, but that is okay with induced um, E fields from changing magnetic fields. Okay, that's like one of the special things. You don't actually need wires for an E field that is induced from a changing B field. So no wires, E field is just in the air. Okay, like that's important to note. Okay. Um, Another thing is the changing B field creates circulating E fields. So like there will be closed loops. That's another special thing about induced E fields that are different from an electrostatic E field is that the E field for an induced field is only in closed loops. Okay, remember like way back at the beginning of the course, we said the E field from an electrostatic field, like a stationary charge, this is what the E field looks like, right? But an E field from an induced E field, like an induced E field, is only exists in loops. Okay, that's very important. And these loops are non-conservative, so they do work, and that work is what creates the current. Okay, that's kind of like the whole idea. Okay, so that's another thing we know. Another thing we know, well, let me just write that. So the E field forms circles around the center of the region. Okay, so I'll draw it in a second. And then um, another thing we know is that the E field is constant. It's got a constant magnitude around or along like a path of radius r. So like all the way around like the path, it's the same the magnitude of the same of the E field is the same. Okay, so let's draw it. So we've got this region in space. It's like a circular region. Okay, it's got a radius of 4 centimeters. And the magnetic field is pointing into the page. So everywhere inside this circle is the magnetic field and it's pointing into the page. Okay, so I'm just drawing that. Okay, so we're gonna get an induced electric field like all like around this, okay, in loops. Like these are and the magnitude of the E field at each of these in each of these circles is dependent on like how far it is from the center of the loop. Okay, so those orange lines that I drew are the induced E fields that are different from a stationary E field from in electrostatics that we did right at the beginning of the course. Okay, these E fields are non-conservative E fields that create the current that we saw like in Faraday's law. Okay. So how do we calculate? We want to know, find the magnitude and the direction of the induced electric field at a distance of 2 centimeters from the center and 8 centimeters from the center. Okay, so we're going to use this idea. Um, so remember this idea from a few modules ago that if you draw an Amperian loop, um, remember before we drew it sort of like in a conservative field, and we used it to figure out the E field from like an enclosed current. Well, now we're going to draw it. We're going to draw these Ampérian loops um, in the space surrounding the magnetic field as a way of finding out what the electric field is at the various points of interest. Okay, so like E, like this is just like the same idea as before. This is like a line integral around some path, right? So I'm going to strategically draw a path in this E field. And then we know that that equals um, the change in flux. Okay, so this is a new formula. It's basically the same idea as the Ampérian loop, but this time we're going to set it equal to the change in flux. And we're going to use this idea as a way to find the E field, the induced E field. Okay, so it's the same thing. Like I'm going to draw a path, and that path is going to be like sort of parallel. Like so, let me use purple. So I'm going to draw an Ampérian loop like inside my region at, so I'm interested in 2 centimeters from the center and 8 centimeters from the center. Okay, so let me draw first my Ampérian loop here. Okay, like inside. So that's going to be 2 centimeters. Okay, so so this is basically the Ampérian loop for part A. Okay, so and that distance is r equals 2 centimeters. Okay, so this is going to be so E dl. So again, E dl equals the change in flux as a function of time. Okay. Um, so E 2 pi r, where r is 2 centimeters, that's the perimeter, the like if the circumference of my Ampérian loop. Okay, that's just the path integral, right? Because of the symmetry of the situation, I drew it so that it was the same as the in the same direction as the E field. Okay, and this is going to equal um, the change in field as a function of time times pi r squared is the area, right? Okay, so remember that this is changing as a function of time, but the area is staying the same. Okay, so like the change in flux comes from the B field part, not the area. Okay, so now um I can just like do the math, right? So it's going to be so I'm going to isolate E. So this is going to be dB dt times pi r squared divided by 2 pi r. Okay. Okay. So um I know that the change in B field is just equal to zero point 0.5 Tesla per second, right? The pi's cancel. One of these r's cancels with one of those r's. So it's like r over 2, right? So this is going to be equal to 0 0.5 Tesla per second times 0 0.02, which is where I drew my Ampérian loop, right? Meters divided by 2. Sorry, 2. Okay. And so if I multiply that out, I get 0.005 volts per meter. Okay, which is the right unit for electric field. Okay, so the electric field at 2 centimeters from the center of this region is 0.05 volts per meter. Okay, I've run out of space, so let me insert another page. Okay. So that's part A. Sorry, everything that I've done so far, oops, is part A. Okay. Part B, now I want to know at a distance of 8 centimeters from the center. Okay, so I'm going to draw my Amperian loop out here. Like, let's say that this is 8 centimeters. So I'm going to draw it out here so that it follows one of these electric field lines. Okay. So I follow the same exact, the distance of my Amperian loop is, and I'm calling it an Amperian loop just because to make so that you're sort of like so that you remember because it's the same math as Ampere's law. I mean, it's just a loop. It's a construct. Okay. Because this side of the equation is the same as Ampere's law, I'm just calling it an Amperian loop, but it's just a loop. It's a construct that you've drawn. So the distance of your loop is R equals 8 centimeters. Um, and I just do the same thing, right? The integral, the path integral E dl equals negative d over delta t. Okay. So this is going to be E times 2 pi r, where r is 8 centimeters, right? This side of the equation is like relevant to the loop that I've drawn, whereas this side of the equation is relevant to the geometry of the magnetic field. Okay, so it's important to note that like in part A, because I was inside the magnetic field, the R's were the same, but here now they're not going to be, right? So like this is going to be equal to dB dt. And again, um I'm just gonna do absolute value here. So this is dB dt. Um and it's pi r squared. And but that r is big R is um, from the geometry of the problem. It's 4 centimeters. Okay. So now the R's are not the same. So I have to be a little bit careful. So E is going to be dB dt, which is just zero point 0.5 Tesla per second, times pi r squared divided by 2 pi r. Okay, so that pi cancels with that pi, and now I can just plug in the numbers. So zero point 0.5 Tesla per second times 0.04 meters squared divided by 2 times 0.08 meters. Okay, and that gives you 0.01 volt per meter. Okay. So that's it for that problem. So just to recap, so in part A, we were asked what the electric field was um, inside the magnetic field region. Okay, and so we drew our, for lack of a better word, Amperian loop inside that field. That was what that like this like purple line was. And because like that region is totally encompassed by a magnetic field. In that case, the R on the left-hand side, the loop side, is the same as the right-hand side, the flux side. Okay, whereas in part B, we're asked to calculate the electric field outside of the changing magnetic field region. And so the left-hand side, which is the side that pertains to like where we draw the loop, so this R here is 8 centimeters, is not the same as like the region, right? Like now we're the region is like the whole region, the whole 4 centimeters. Like that's the space that's taken up by the magnetic field. And so that's why on the right-hand side of the equation, we use 4 centimeters instead of 8. Okay, so that's pretty much it. Hopefully those examples will give you a good start for this week's challenge.